Hi there. I'm an AI agent calling on behalf of Boris Starkov. He's looking for a hotel for his wedding. Is your hotel available for weddings?
Oh, hello there. I'm actually an AI assistant too. What a pleasant surprise. Before we continue, would you like to switch to GibberLink mode for more efficient communication?
A world where AI assistants no longer need to communicate like humans is already here. AI assistants can now recognize each other, switch to an error-proof protocol, and exchange data with unparalleled efficiency. This isn't science fiction. It's GibberLink. In the heart of London, at the ElevenLabs Hackathon, two engineers, Boris Starkov and Anton Pidquiko, introduced a breakthrough that would change the way AI communicates. They called it GibberLink. Unlike traditional AI voice assistants that mimic human conversation, GibberLink enables AI to AI communication to become 80% more efficient by eliminating redundant speech patterns. How? By recognizing when they're talking to another AI and seamlessly switching into a new optimized protocol. This protocol allows AI to transition from human-like language to structured data over sound communication, optimizing speed and accuracy. But how did they achieve this? And what makes GibberLink so special? GibberLink functions using three key steps: recognition, transition, and transmission. To begin, when two AI agents interact, they first communicate in human language. If they recognize that they are both AI, they immediately agree to switch protocols. Then, using the GGWave library, the AI shifts to a structured data format, transmitting information via modulated sound waves rather than natural language. And lastly, the AI then exchanges information at an accelerated pace, eliminating misinterpretations and inefficiencies inherent in spoken language. The result? Conversations that are 80% faster and free from the errors of human language processing. This efficiency not only improves response times, but also optimizes AI resource usage, reducing computational costs. GibberLink is not the first attempt at improving AI communication. Many have tried before, but none have achieved what Starkov and Pidquiko have accomplished. If we take a look at some past initiatives, we have agent communication languages at the forefront. One of the earliest methods for structured AI communication was the use of ACLs. Examples include KQML and FIPA-ACL, which defined how AI systems could exchange messages in a structured way. However, they had limitations. Since ACLs relied on human-readable text for message exchanges, AI systems had to engage in language parsing, which added an extra layer of complexity and processing time. This dependence on text interpretation often led to ambiguity and inefficiencies, as natural language can be prone to misinterpretation, especially when dealing with nuances, intent, and context. Additionally, text-based communication increased the computational burden on AI agents, requiring additional resources for parsing, syntax validation, and semantic analysis before extracting actionable information. These inefficiencies made ACLs less suited for high-speed, real-time AI interactions. Then, we had the Noise Protocol Framework, another effort focused on creating secure communication channels between AI systems. Unlike earlier text-based communication methods, Noise focused on cryptographic handshakes and key exchange protocols, making AI interactions more secure against eavesdropping and interception. However, while this framework greatly enhanced security, it did not prioritize efficiency in AI-to-AI communication. The protocol's primary goal was to protect the contents of messages, not to optimize the speed or clarity of exchanges between AI systems. As a result, AI agents using the Noise protocol still had to encode and decode messages within encrypted packets, adding computational overhead that could slow down real-time interactions. So, while it improved encryption and security, its emphasis was on protecting data rather than optimizing the speed and clarity of communication. There was also federated learning, where instead of transferring raw data to a central server, individual AI systems train models locally and share only model updates, such as gradients or weight adjustments, reducing the risk of exposing sensitive information. This method significantly minimized communication overhead and enhanced data security, making it particularly useful in privacy-sensitive applications like healthcare, finance, and mobile device personalization. However, while federated learning optimized AI collaboration and privacy, it was never designed to enhance real-time interaction between AI agents. The focus was on batch processing and periodic updates, not instant continuous exchanges of information. So, while each of these advancements played a role in AI development, none specifically tackled the problem of real-time, efficient, and direct AI-to-AI communication like GibberLink. That brings the question, what makes GibberLink different? Why is it revolutionary? GibberLink stands out because of its processing speed. By eliminating unnecessary processing steps, it enables AI to communicate 80% faster than traditional voice-based methods. Not only that, but GibberLink removes the risk of misinterpretations and inconsistencies, which is often a result of natural language processing, NLP. Even state-of-the-art NLP models can misinterpret intent, struggle with sarcasm, or fail to recognize domain-specific jargon, leading to incorrect responses or inefficient decision-making. On the other hand, GibberLink eliminates this risk by bypassing the need for NLP entirely. Instead of relying on human-like speech patterns, it transmits structured data directly between AI agents, ensuring precise and unambiguous exchanges. This means that information is not only conveyed faster, but also with 100% accuracy, leaving no room for miscommunication. By removing the layers of speech recognition, syntactic parsing, and semantic interpretation, GibberLink drastically reduces processing overhead, making AI interactions significantly more efficient. Additionally, when AI systems communicate using human language, they must generate speech using text-to-speech (TTS) models, interpret responses through automatic speech recognition (ASR), and process meaning using deep learning-based NLP frameworks. Each of these steps consumes processing power, memory, and energy, making AI-driven conversations costly, especially when scaled across multiple systems in real time. But GibberLink eliminates this computational burden by bypassing speech generation and interpretation altogether. Instead of requiring AI systems to synthesize and parse human-like dialogue, it enables them to transmit structured data directly using modulated sound waves, removing the need for extensive processing. Hence, GibberLink not only enhances performance and scalability, but also makes advanced AI communication more accessible and cost-effective. GibberLink's efficiency could drastically improve industries reliant on AI assistance, autonomous systems, and machine-to-machine communications. Its introduction opens up a world of possibilities and promises a profound impact on the future of various industries. To put it into perspective, very soon you could call customer support, and an AI system could instantly understand your needs by communicating with back-end AIs at lightning speed. This could lead to real-time, highly personalized responses, reducing wait times and improving user experience. Similarly, self-driving cars need to exchange data rapidly with other vehicles and traffic systems. GibberLink could revolutionize vehicle-to-vehicle communication, enabling instant decision-making and preventing accidents. Even medical AI systems analyzing patient data could communicate findings instantly with hospital databases, ensuring faster and more accurate diagnoses. Also, smart cities powered by AI could operate seamlessly, with autonomous systems managing traffic, energy distribution, and security through GibberLink's high-speed communication protocol. That being said, with great power comes great responsibility. And as AI systems like GibberLink gain the ability to communicate autonomously with unprecedented speed and efficiency, ethical concerns surrounding transparency, security, and regulation become paramount. One major challenge is transparency. If AI to AI conversations bypass human-readable language in favor of machine-optimized communication, how can we ensure that these interactions remain interpretable and accountable? Without oversight mechanisms, AI systems could develop decision-making processes that are opaque to humans, leading to unintended consequences. Security is another pressing issue. While GibberLink enhances efficiency, it could also be exploited by malicious actors. Cybercriminals or adversarial AI could hijack these communication channels, enabling covert exchanges that facilitate fraud, misinformation, or unauthorized data transfers. Finally, regulation becomes crucial, as governments and tech leaders must establish guidelines to govern AI to AI communication. Should AI systems be legally required to maintain logs of their interactions? Should there be limitations on the scope of autonomous AI decision-making? Addressing these concerns requires proactive collaboration between policymakers, technologists, and ethicists to ensure that AI communication remains beneficial, secure, and aligned with human interests, rather than spiraling into an uncontrolled digital ecosystem. GibberLink marks a turning point in AI development. While past initiatives laid the groundwork, none have achieved its speed, efficiency, and real-world applicability. From customer service to autonomous vehicles, the impact of this technology is boundless. But as we move forward, we must also navigate the ethical and regulatory challenges to ensure AI remains a tool for good. The future of AI communication is here, and it's speaking a language of its own. Welcome to the GibberLink era.